Derating factor specified in 310.15b fork of the National Electrical Code stems from research indicating that harmonics can elevate conductor temperatures within electrical systems. The extent of derating hinges on the degree of harmonic distortion present. In situations where measured harmonic distortion remains below the threshold necessitating derating, the code does not mandate it. However, the derating factor in 310.15b fork is a minimum requirement. Over and above the minimum requirement, you can choose to implement a more conservative derating strategy to bolster system safety and reliability. Awareness of potential harmonic effects on electrical systems is crucial. Employing larger conductors and conduits proves beneficial in minimizing the risk of conductor overheating and associated issues triggered by harmonics. Consistent monitoring of harmonic distortion levels within the system is advisable. Escalation in harmonic distortion may necessitate supplementary measures to alleviate harmonic-related consequences. When considering harmonic derating, several factors come into play. Firstly, the type of load significantly influences the harmonic content. Nonlinear loads such as variable frequency drives, electronic ballasts, and switching mode power supplies generate harmonics. Secondly, the system impedance affects harmonic propagation. Lower impedance paths facilitate harmonic current flow. Thirdly, conductor sizing plays a crucial role in managing heat generated by harmonic currents. Fourthly, a neutral conductor's role in carrying harmonic currents, particularly tripling harmonics, should be carefully evaluated. Fifthly, transformer derating may be necessary to account for increased losses due to harmonic currents. Sixthly, harmonic filters can be implemented to reduce harmonic distortion levels. Seventhly, power factor correction capacitors can exacerbate harmonic problems if not properly applied. Eighthly, regular monitoring of harmonic levels is essential to ensure system performance. Ninthly, compliance with IEEE 519, which recommends limits on harmonic voltage and current distortion on power systems, is important. Tenthly, proper grounding practices help to minimize harmonic-related issues. To elaborate, harmonics are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. The most common harmonics are the odd-numbered harmonics, such as the third, fifth, and seventh. Even-numbered harmonics are generally less prevalent in power systems. Tripling harmonics, which are odd multiples of the third harmonic, are particularly problematic because they are additive in the neutral conductor of a three-phase system. This can lead to neutral overload and overheating. The amount of harmonic distortion in a system is typically quantified by total harmonic distortion, THD, which is the ratio of the root mean square, RMS, value of the harmonic content to the RMS value of the fundamental frequency. IEEE 519 provides recommended limits for THD based on the system voltage and the size of the load. The NEC requires conductors to be sized to carry the expected load current. However, in systems with significant harmonic distortion, the conductor current can be higher than the load current due to the presence of harmonic currents. Therefore, it is necessary to derate the conductors to account for the additional heating caused by the harmonic currents. The derating factor specified in 310.15b fork is based on the percentage of the load that is nonlinear. If the load is 50% or more nonlinear, the conductors must be derated to 80% of their ampacity. If the load is 100% nonlinear, the conductors must be derated to 70% of their ampacity. In addition to derating the conductors, it may also be necessary to derate the neutral conductor. As mentioned earlier, tripling harmonics are additive in the neutral conductor. This can cause the neutral conductor to carry more current than the phase conductors. If the neutral conductor is not sized properly, it can overheat and fail. The NEC requires the neutral conductor to be sized to carry the maximum unbalanced load current. However, in systems with significant harmonic distortion, the neutral conductor may need to be sized larger than the maximum unbalanced load current to account for the tripling harmonics. Transformers are also affected by harmonics. Harmonic currents cause increased losses in the transformer core and windings. These losses can cause the transformer to overheat and fail. Therefore, it may be necessary to derate the transformer to account for the harmonic currents. The amount of derating depends on the transformer design and the level of harmonic distortion. Harmonic filters can be used to reduce harmonic distortion levels. Harmonic filters are typically installed at the load that is generating the harmonics. Filter is designed to shunt the harmonic currents away from the power system. There are two main types of harmonic filters: passive filters and active filters. Passive filters consist of capacitors and inductors that are tuned to resonate at a specific harmonic frequency. Active filters use electronic components to generate harmonic currents that are equal in magnitude but opposite in phase to the harmonic currents generated by the load. This cancels out the harmonic currents and reduces the harmonic distortion levels. Power factor correction capacitors can exacerbate harmonic problems if not properly applied. Capacitors are used to improve the power factor of a system. However, capacitors can also resonate with the system inductance at a harmonic frequency. This can cause the harmonic currents to be amplified, which can lead to increased harmonic distortion levels. Therefore, it is important to carefully design and apply power factor correction capacitors in systems with significant harmonic distortion. Regular monitoring of harmonic levels is essential to ensure system performance. Harmonic levels can change over time due to changes in the load or the system configuration. Therefore, it is important to monitor harmonic levels regularly to ensure that they are within acceptable limits. Harmonic monitoring can be performed using a power quality analyzer. A power quality analyzer is a device that measures voltage, current, and harmonic distortion levels. Data from the power quality analyzer can be used to identify harmonic problems and to verify the effectiveness of harmonic mitigation measures. Compliance with IEEE 519 is important. IEEE 519 recommends limits on harmonic voltage and current distortion on power systems. These limits are designed to protect equipment from the harmful effects of harmonics. Compliance with IEEE 519 can be achieved by implementing harmonic mitigation measures such as harmonic filters and by properly sizing conductors and transformers. Proper grounding practices help to minimize harmonic-related issues. A properly designed grounding system provides a low impedance path for harmonic currents to flow back to the source. This helps to reduce voltage distortion and to protect equipment from harmonic-related damage. In summary, harmonics can have a significant impact on electrical systems. It is important to be aware of the potential effects of harmonics and to take steps to mitigate these effects if necessary. This can be achieved by implementing harmonic mitigation measures, by properly sizing conductors and transformers, and by following proper grounding practices. Here's a more detailed breakdown of specific considerations. Firstly, conductor sizing is paramount. When dealing with harmonic currents, conductors must be sized not only for the fundamental frequency current, but also for the additional heating caused by harmonic currents. The National Electrical Code, NEC, provides guidelines for derating conductors based on the number of current-carrying conductors in a raceway or cable, as well as the ambient temperature. In harmonic-rich environments, these derating factors may need to be further adjusted to account for the increased heating. Secondly, neutral conductor loading requires careful attention. In three-phase, four-wire systems, triplet harmonics, which are odd multiples of the third harmonic such as the third, ninth, and 15th, are additive in the neutral conductor. This can result in a neutral current that exceeds the phase currents. The NEC addresses this issue in 220.61, which requires the neutral conductor to be sized to carry the maximum unbalanced load, including the harmonic currents. Thirdly, transformer derating is essential. Transformers are susceptible to overheating due to harmonic currents, which cause increased core and winding losses. The K-factor is used to specify the transformer's ability to withstand harmonic currents. A transformer with a higher K-factor can handle more harmonic current without overheating. If the harmonic content is significant, it may be necessary to use a K-rated transformer or to derate a standard transformer. Fourthly, harmonic filtering offers a mitigation strategy. Harmonic filters are designed to reduce harmonic distortion by providing a low impedance path for harmonic currents. Passive filters consist of tuned capacitors and inductors that are designed to attenuate specific harmonic frequencies. Active filters use electronic components to inject harmonic currents that are equal in magnitude but opposite in phase to harmonic currents generated by the load, thereby cancelling out the harmonics. Fifthly, power factor correction capacitors can exacerbate harmonic resonance. Power factor correction capacitors can create a resonant condition with the system inductance at certain harmonic frequencies. This can amplify harmonic currents and voltages, leading to equipment damage. To prevent this, reactors can be installed in series with the capacitors to detune the circuit and avoid resonance. Sixthly, grounding and bonding are critical. Proper grounding and bonding are essential for minimizing harmonic-related problems. A low-impedance ground path is necessary to safely carry harmonic currents back to the source. The NEC specifies grounding requirements in Article 250. Seventhly, harmonic measurement and analysis should be performed regularly. Harmonic distortion levels can vary over time due to changes in a load or system configuration. Regular harmonic measurement should be taken to monitor harmonic levels and to ensure that they are within acceptable limits. A power quality analyzer can be used to measure voltage, current, and harmonic distortion levels. Eighthly, compliance with IEEE 519 is important for maintaining power system quality. IEEE 519 provides recommended limits for harmonic voltage and current distortion on power systems. These limits are designed to protect equipment from the harmful effects of harmonics. Compliance with IEEE 519 can be achieved by implementing harmonic mitigation measures and by properly sizing conductors and transformers. Ninthly, adjustable speed drives are a common source of harmonics. Adjustable speed drives, also known as variable frequency drives, VFDs, are widely used to control the speed of motors. However, they are also a significant source of harmonics. VFD use pulse width modulation (PWM) to control the motor voltage and frequency. This process generates harmonic currents that can propagate throughout the power system. Tenthly, lighting systems can also contribute to harmonic distortion. Electronic ballasts used in fluorescent and LED lighting systems can generate harmonics. The harmonic content of these ballasts varies depending on the design and quality of the ballast. High-quality electronic ballasts typically have lower harmonic distortion levels. Here are some additional considerations for addressing harmonics in electrical systems. Firstly, understanding harmonic sources is crucial. Identifying the specific equipment or processes that are generating harmonics is the first step in developing a mitigation strategy. Common harmonic sources include variable frequency drives, electronic power supplies, uninterruptible power supplies, UPS, and arc furnaces. Secondly, assessing harmonic levels is necessary for proper evaluation. Measuring harmonic voltage and current distortion at various points in the electrical system provides valuable data for assessing the severity of the harmonic problem. This data can be used to determine whether harmonic mitigation measures are necessary. Thirdly, implementing mitigation techniques is part of the solution. Various techniques can be used to mitigate harmonics, including harmonic filters, line reactors, and phase-shifting transformers. The choice of mitigation technique depends on the specific characteristics of the harmonic problem. Fourthly, monitoring system performance post-mitigation is important. After implementing harmonic mitigation measures, it is important to monitor the electrical system to ensure that the mitigation measures are effective and that harmonic levels are within acceptable limits. Fifthly, considering future expansion is critical. When designing an electrical system, it is important to consider the potential for future expansion and the impact that this expansion may have on harmonic levels. This can help to avoid harmonic problems in the future. Sixthly, proper component selection is important for system longevity. Selecting electrical components that are designed to withstand harmonic currents can help to improve the reliability and lifespan of the electrical system. This includes selecting transformers, conductors, and circuit breakers that are rated for harmonic service. Seventhly, professional consultation can provide key expertise. Consulting with a qualified electrical engineer who specializes in power quality can provide valuable assistance in addressing harmonic problems. An engineer can perform a harmonic study, recommend mitigation measures, and oversee the implementation of these measures. Eighthly, staff training is important for proper operations. Training electrical staff on the basics of harmonics and the importance of power quality can help to prevent harmonic problems and to ensure that the electrical system is operated safely and efficiently. Ninthly, regular maintenance can improve system quality. Regular maintenance of electrical equipment can help to reduce harmonic levels and to improve the overall power quality of the electrical system. This includes cleaning equipment, tightening connections, and replacing worn components. Tenthly, documentation practices are important for future referencing. Maintaining accurate documentation of the electrical system, including harmonic measurements and mitigation measures, can be helpful for troubleshooting problems and for planning future upgrades. Let's delve into the implications of 310.15b fork further. Firstly, the purpose of 310.15b fork is to address the potential for increased conductor heating due to harmonic currents. Harmonic currents can cause conductors to overheat, which can lead to insulation breakdown and other problems. The derating factors in 310.15b fork are designed to reduce the risk of conductor overheating. Secondly, the scope of 310.15b fork applies to conductors that carry power to nonlinear loads. Nonlinear loads are loads that draw current in a non-sinusoidal manner, such as variable frequency drives and electronic power supplies. The derating factors in 310.15b fork only apply to conductors that supply these types of loads. Thirdly, the derating factors in 310.15b fork are based on the percentage of the load that is nonlinear. The more nonlinear the load, the greater the derating factor. For example, if a load is 50% nonlinear, the conductors must be derated to 80% of their ampacity. Fourthly, the derating factors in 310.15b fork are cumulative with other derating factors. If conductors are also subject to other derating factors, such as those for ambient temperature or the number of current-carrying conductors in a raceway, the derating factors must be applied cumulatively. Fifthly, the neutral conductor may need to be oversized to carry harmonic currents. In three-phase, four-wire systems, triplet harmonics are additive in the neutral conductor. This can cause the neutral conductor to carry more current than the phase conductors. If the neutral conductor is not sized properly, it can overheat and fail. Sixthly, harmonic filters can be used to reduce the need for conductor derating. Harmonic filters can reduce the amount of harmonic current flowing through the conductors, which can reduce the need for conductor derating. Seventhly, K-rated transformers can withstand harmonic currents without derating. K-rated transformers are designed to withstand the heating effects of harmonic currents. If a K-rated transformer is used, the conductors do not need to be derated for harmonic currents. Eighthly, the NEC allows for alternative methods of conductor sizing in some cases. The NEC allows for alternative methods of conductor sizing if it can be demonstrated that the conductors will not overheat under the expected loading conditions. This may require a detailed harmonic analysis. Ninthly, documentation of conductor sizing calculations is important. It is important to document all conductor sizing calculations, including the derating factors that were applied. This documentation can be helpful for troubleshooting problems and for planning future upgrades. Tenthly, professional judgment should be used when applying 310.15b fork. The application of 310.15b fork requires professional judgment. The specific derating factors that are applied should be based on the specific characteristics of the electrical system and the loads that it serves. In conclusion, addressing harmonic concerns involves a multifaceted strategy. This encompasses precise conductor sizing, cautious neutral conductor management, transformer derating considerations, strategically implemented harmonic filtering, awareness of capacitor-induced resonance, rigorous grounding methodologies, regular measurement and analysis, adherence to IEEE standards, proactive mitigation for adjustable speed drives, and mindful handling of lighting system contributions. Through the comprehensive application of these considerations, electrical systems can effectively minimize the adverse impacts of harmonics, ensuring dependable and secure operation.